let's recognize the transformations that are involved in this function. What we have here is 1/2 sine of x minus 3/2. So first thing, this entire function has that main function sine of x being involved here. So I am going to compare this with my original or my ordinary sine of x, the standard sine of x. So to compare with the sine of x, we notice there's a coefficient m multiplied in front of the sine of x here, and that m in this case is being a 1/2. And so I'm sure this 1/2 is going to change the amplitude, so I am expecting some amplitude change here. Because we have an m value being a positive 1/2. And besides, we have this function subtracting a constant. And so after seeing this subtraction, we are expecting some center line change. And so now back to our original function, sine of x. Amplitude on this ordinary function is 1. And we learn here that the amplitude, when we have the coefficient m being multiplied to the function, is absolute value of m. So in this case, we have an absolute value of 1/2, which is 1/2. So amplitude of this graph here has to be a 1/2 compared to the original graph, or compared to the graph of the ordinary sine of x. Since our m here is being a positive, so make a note here, there are no reflections. No reflection compared to the original version. Our original sine of x has center line at y equals 0, or the x-axis. And since our function here, after looking at the amplitude, our function here has that subtraction. We subtracted a minus 3/2 on that, so the center line here is now changed to y equals negative 3/2. And if we're looking further into the inside of our sine function, then the inside of this current sine function looks exactly the same as the inside of our ordinary sine of x function. So on the ordinary sine of x, the period is 2 pi. And so here we expect no period change. The period on this function remains exactly the same due to that expression inside being exactly the same. Our function here, the ordinary function, or the original standard sine of x function, has the start at x equals 0, and it has an end at x equals 2 pi. And so since our function here currently has the inside of sine function looking exactly like the original sine, so as far as the start on our base unit, we expect no change as well. So it's the same start, x equals 0, compared with the original. And the end here, of course, is simply from where the start is, we're adding with the period, in this case 2 pi, so that gives us the end of our current function here. The end of our base unit is at 2 pi. So also blended with the new terminologies we've learned here, then since this function has no change in the start and end, we are saying that we got no phase shift, and as well as no period change. Let's now confirm the transformation we recognized in the function 1/2 sine of x minus 3/2 by looking at the graphs. And so once again, here's the graph of the ordinary sine of x function in red color. And currently we're only looking at the base units of this ordinary sine of x function. And so, as we already knew, the center line is here on the x-axis, the amplitude being 1. So for that reason, the wave here goes up and goes down only 1 on each way from the center line. And the period being 2 pi, so we have a start at 0 and the ending at 2 pi over here. And so now our graph, the base units for our 1/2 sine of x minus 3/2 is here in blue ink. The center line is at negative 3/2. So here it is, the line in the dotted black ink right here. And what we confirm, so the first thing we confirmed was the center line was down at negative 3/2, which is right here. And the amplitude of this blue wave is only 1/2. So from where the center line here is, the blue wave only 1/2 up and down from where the center line is. And other than that information, the blue wave remains the same period window with our ordinary sine of x. And also the blue wave here is having the start and the end being the same as the start at the end on the base units of our ordinary sine of x. And so now in the complete view of each of our function here, sine of x in its complete view is here. And now 1/2 sine of x minus 3/2 in its complete view is now here. Here, let's recognize the transformations that are being involved in this function here. Y equals minus 2 cosine of x plus 1/4. So right from the start, this function has that cosine of x as the main function being involved. So I am going to compare this entire function with my original or ordinary cosine of x function. And many other times I refer to as the standard cosine of x in many of my other video lessons. And so looking into the two functions here, then compare with the original cosine of x, my current function here, cosine of x here, has a coefficient minus 2 in front. And so right here, tackling down that minus 2 as a coefficient, then I am expecting some amplitude change. And then comparing with my original cosine of x, there was no constant being added or being subtracted from this cosine function. And here I have a constant being added to my cosine of x, to my minus 2 cosine of x. So in that case, I am expecting some center line change. So that plus 1/4 is responsible for changing the center line. So those are the two changes being expected in this function compared to the original cosine of x. And so let's tear it down one by one right here. Amplitude of the original cosine is known to be 1. And as we have learned already, since we have a coefficient multiplied with our function cosine of x, then the amplitude this time, the amplitude on our current function, and here I have to note that m equals negative 2. So our amplitude here is absolute value of m. So consequently, absolute value of negative 2, or the amplitude for our function here, is a positive 2 compared to the original ordinary cosine of x having amplitude 1. A further note is that since this m we have here, our coefficient is a negative coefficient, then we do have some reflection. So here our graph is reflected through the x-axis. So that's another detail we noticed. So this coefficient has a lot of changes to the graph of cosine of x. Back to our original cosine of x, the center line is at y equals 0. And here, center line of our current function here, since we had that constant 1/4 being added to our function, then center line is changed to the line y equals a positive 1/4. So we recognize two transformations being involved here, two changes being caused compared to the original cosine of x function. And for all the remaining parts, period on the original cosine, it's 2 pi, and we refer to that as a standard period. The period on our current function here, since the inside of our cosine is looking exactly like the inside of our cosine, our original cosine, and so we expecting the same period or no period change. The inside of our cosine of x function here once again looks exactly like the inside of our original cosine of x. So the start on the original cosine of x is known to be x equals 0, and the end on the original cosine of x is known to be at x equals 2 pi, and so nothing changed here on our current function. As I explained earlier, the inside of our cosine function here looks exactly like the inside of our cosine function on the original version, and so here we're gonna expect our start to remain the same, and remain the same compared to the original graph. And once again, the start here is the start on our base unit, on the base unit of this particular function, and the end of the base unit is once again x equals the start plus the period 2 pi. In this case, that equals 2 pi. And so another example we can see here, and we can see here that in this problem there are no phase shift due to the start and the end of the same. The start of the base unit is nothing different with the start of the base unit on the original cosine function. And now let's confirm the transformations we recognized in our function minus 2 cosine of x plus 1/4. And so in my red color, cosine of x in its base unit is here. And once again, we recognize that for this ordinary cosine of x, then the center line is at y equals 0, or namely the x-axis. And having that amplitude being 1, this wave for cosine of x, the ordinary cosine of x, goes up and down 1 on each way from the center line. And period being 2 pi, with the start of the base unit at 0 and the end of the base unit at 2 pi. So now in blue color, the base unit of my minus 2 cosine of x plus 1/4 is here. And so now the center line, as we have recognized, was being a 1/4. And so now I'm going to bring up that center line here in dotted black color right here. And so this center line in black color, we can see that our wave this time is being reflected through this center line in black color here. And so, and from where this center line here being in black, then the wave of our blue negative 2 cosine of x plus 1/4 here, in this wave is the estimation is showing that it's 2 on each way. It's going up and down by 2 each way from where the center line is. And so that is all consistent with the transformations we have recognized. So we recognize that it had a change in the amplitude, being more than the amplitude of the ordinary function. And then it has that reflection through the center line. And furthermore, it has that shift in the center line being from where ordinarily 0, but now shift to y equals 1/4. And other information as far as period remains the same. So the same windows from the start of the base units to the end of the base units is being that same interval length compared to the periods of our ordinary cosine of x in red here. And so now in complete view, this is our complete cosine of x. And in complete view, this is our complete -2 cosine of x plus 1/4. All right, so let's now recognize the transformation that are involved in this function. So we have here y equals cosine of -2x minus pi over 3. So since our function here is being a cosine function, let's briefly review for ourselves about the ordinary cosine of x function. So our ordinary cosine has these properties right here. We know the amplitude of ordinary cosine equals 1. The period of ordinary cosine equals 2 pi. The center line of ordinary cosine is at y equals 0. We have the start of the base unit on our ordinary cosine being at x equals 0. And the end of the base unit of our cosine of x is at 2 pi. And so the expression inside of our cosine function here in this actual problem is a linear expression, a lot different from this expression inside of our ordinary cosine function. And so we have learned that when our expression inside of the cosine being a linear expression like this, then we can do a quick little separate side work here, but I'm going to factor out. So starting with -2x minus pi over 3, I am going to factor out the -2. And so that's what we have learned. That's what we've learned that we need to do. So -2 in parentheses, now I have x plus a pi over 6. What this does to our current function now is that we can now substitute this into our current cosine function in place of the -2x minus pi over 3. And so here we have -2 in parentheses x plus pi over 6. And here we're recognizing that we have this 2 here with the negative sign is responsible for the changes in the period. And it could possibly cause some reflection through the x-axis as well. And we're going to find out this value right here, pi over 6, is now clearly recognized as bringing changes to the starts and the end of the base units. And all this here changes to the start and the end of the base units. It's generally refers to as it's going to bring some phase shift. Some phase shift is going to happen here. All right, so recall from our learning on the elementary transformation apply in a trig function, then this -2 in front of the parentheses here can be thought of as an a value being +2 and -2 here is a -a. And so this will immediately tell us that the period on this function, on our current function, cosine of -2x minus pi over 3 has period from the standard period of the ordinary cosine. We are going to divide by 2 from this a value, and that consequently reduces down to pi. So this function of ours is having the period pi. We also learned that when our expression here has an x plus a positive value, we can recognize that we have a value b here. The positive value b in our expression here is a pi over 6. So we have learned that it's going to cause a change to the start of our base unit. So our base unit now is starting at minus pi over 6. And again, once we recognize the start of the base unit and as well as the period, the end of the base unit can be easily found by simply x equals, from where our start value is, we are going to add with the period amount. And that comes up. Our calculation shows that it should be 5 pi over 6. So this is the end and this is the start. And in a formal term, start and end of our base units being different from start and end of the ordinary cosine, all this here is referred to as a phase shift. So we have a phase shift being pi over 6 shift to the left hand side. On this function, even though we had a minus a, but our function being a cosine, which is an even function. So recall from that property, and I mentioned this in our lecture about the elementary transformations, but cosine of a negative expression is the same with the cosine value on a positive expression. So in the end, having a negative here will not, in other words, we will not have any reflection on the x-axis. So no reflection, and I should have said through the x-axis. So no reflection through the x-axis. And so, other than the two transformations being recognized earlier, then this function, everything else remains the same as the original or the ordinary cosine of x function, meaning amplitude of this function is simply 1. The center line is at y equals 0, or the x-axis, due to this function did not have any constant term added or subtracted from to the function. Now we can confirm the transformations we have identified in our function cosine of minus 2x minus pi over 3 by looking at its graph. And once again, the graph in red color now is the original or ordinary cosine of x, and this is only its base units from between 0 to 2 pi. And so the graph for cosine of minus 2x minus pi over 3 is now here in the blue color. And so we notice there are some changes. So first of all, as far as the fundamental shape, it looks the same again, but this blue graph for cosine of minus 2x minus pi over 3 is a lot shorter in terms of the wavelength. And so this blue graph here has a start, and of course this is the base units of our cosine of minus 2x minus pi over 3. And so this base unit on the blue graph has a start at minus pi over 6, as the grid on my graphing system here is showing, and it has an end at 5 pi over 6 here. And so totally that space, or that horizontal distance being the period of this blue wave here, is, if we're doing the math, it's exactly pi. And that confirms our transformation we have seen in the functions here. And outside of the period and the start and the end of the base unit here, or in other words, phase shift being recognized here. Other than that, the center line of this graph remains the same compared with the center line of the original ordinary cosine of x. The amplitude of this wave in blue also remains the same as the amplitude of this wave in red right here. The amplitude here is simply being 1, or this blue wave is only going up and down by 1 on each side of the center line right here. Here's the complete cosine wave right here, and the complete cosine of minus 2x minus pi over 6 is here. And let me put it in a further zoom so that we can all see how it looks. Let's now try to recognize all transformations that are being involved in this function. So what we have here is minus 1/2 as a coefficient times sine of, inside of my sine function I have a linear expression, minus 3x plus pi over 5 and minus 2. So when we really are working with an expression that looks this complicated, before we really try to nail down any transformation being involved here, let's first work on our linear expression inside of our trig function here, and same experience can be extended to any other trig function. So the first thing I'm doing is, once again on the corner of my paper, minus 3x plus pi over 5. What I'm going to do here, I am going to factor out a negative 3 factor. And so my linear expression inside of the trig function now becomes minus 3 in parentheses x minus pi over 15. And once we can make the complete factor of our expression, our linear expression inside of the trig function, then this is what the trig function is going to become. So in the next step, I am going to rewrite our current function as y equals negative 1/2 sine of that linear expression inside of the function now can be rewritten as minus 3 and another sub-level of parentheses is x minus pi over 15 and minus 2. And here at this point, if we're looking a little more closely, the coefficient negative 3 here, it looks like we're almost ready to recognize the transformation, but actually one more step can get things done a lot more easily for us here. But recall that sine of any negative expression. So we're looking at all this factor here as some negative expression. So we've learned that since sine being an odd function, so sine on a negative expression will equals to the negative value of sine of theta. The positive expression now remains inside. The impact of this understanding, and once again this is all due to sine itself as being an odd function. We discussed this in the lecture. And so meaning, or the impact of this understanding, is that now I can bring that negative sign of my negative 3 inside of the sine function here to the front and compensate together with that negative 1/2. So now it all becomes, so in my next step here, my current function will actually become positive 1/2. So once again, it's all due to that nature. We are allowed to bring that negative sign out front and multiply together. So now it's become a positive 1/2 sine of positive 3. Now, since we already brought remember, once we brought the sign out front, this negative sign out front of our sine function, then the expression inside of our sign remains a positive sign. So 3 in parentheses, x minus pi over 15 in parentheses minus 2. But now at this final form, so rule of thumb is always anytime that we run into anytime that our trig function in general doesn't have to be sine, doesn't have to be cosine, but any of our trig function has a linear having a linear expression inside of it with a negative coefficient, with a negative linear coefficient, then we can and then after factoring out that linear coefficient, we can always find a way, take advantage of the odd or the evenness of the function to work on that negative sign to always bring it down to a positive expression inside. So we always want to have a positive expression inside, and there will be a way to get it handled depending on every problem. And so now this final expression for our function, so keep in mind they're all exactly the same function, but now it's a lot more reduced. So here, this form here that we have put our function into, we are now ready to recognize the transformation that appears that are involved in our function. And so now, as we realize that we're currently working with a function that has a sine involved here, that has a sine trigonometry function being involved, then it's a good idea to briefly review the ordinary sine of x function. And so, briefly looking back, anytime we're looking at our ordinary sine function or the standard sine function, then the amplitude was known famously to be 1. The period of this ordinary sine function is 2 pi, and we usually call it, it's a standard period. And this ordinary sine of x function has a center line located at the line y equals 0, or namely the x-axis. And the base units for our sine of x function starts at x equals 0, and the end of our base units of the sine of x graph right here is at x equals 2 pi. So after that brief review or brief looking back right here, then we have learned throughout our lectures on all the elementary transformations, then the coefficients in front of our sine function, outside of the sine function, is the elements that's responsible for, we're going to have some amplitude change. So that's one thing to make note of for the next step. Also, outside of our sine function, we have a constant 2 being subtracted from our function. So this 2 being subtracted from our sine function is going to be responsible for the center line change. So we will run into some change in the center line. And now considering from the inside of our sine functions here, and we have spent some time working on the factoring out the inside linear expression. So now at this point, this coefficient 3 is now responsible for period change. So that coefficient is going to be changing our period amount. And last thing, this value here, pi over 15, is going to be responsible for our starts change, or it's just that we're changing our starting point. And once again, this is also, or another word of saying, is that this subtraction pi over 15 is responsible for a phase shift. And then to make a connection with our lectures on all the elementary transformations, then this 1/2 right here is known as the m of our function. This value 3 that's responsible for the period change is our a value. In this case, already been put as a positive a, being 3. So a equals 3, m here equals 1/2, and this is a minus the b value we are using here in connection with that lecture we've had about making all the elementary transformations. And b here is a positive pi over 15, and then here is a minus c. So our c value responsible for the center line is 2. And now, after having an overview of all the changes from the original sine of x can be expected in this function, then we are now ready to make that final list of all the changes here. So this value, remember we expected it's going to cause some amplitude change. So now our actual amplitude for this function, the rule of the transformation says it's going to be equals to the absolute value of m, which is in this case absolute value of positive 1/2, which is a 1/2. Another thing to note is that our final coefficient m in front of the sine function here, or in front of the trig function in general, is now already a positive value. So we expect no reflection. Through the x-axis. So that's about the amplitude. That minus 2, or that, in other words, that constant 2 being subtracted from our function, is responsible for shifting the center line and consequently brings the entire graph down. So the center line now is being changed to y equals -2. And now let's look at this inside of the function here. So we're now going to have some period change. And the period here, standard period of the ordinary sine of x function is a 2 pi. But due to that coefficient 3, we are going to divide by 3, and it was already positive value, so we just divide by 3. So our final period for this function is expected to be a 2 pi over 3 period. The base unit has a different starting point. So how we can identify that is from this value right here. So the start of our base unit on this function is going to be x equals pi over 15. And this is how formally a lot of people refer to this as we have a phase shift. Our phase shift here is being a pi over 15, or in general we have a phase shift. And so now consequently the ending of this, of the base unit on this function, is going to be from where our starting point is, pi over 15, but we're going to add with the period values 2 pi over 3, and we will consequently come out with, after making common denominator and all that, we adding into 11 pi over 3, and I mean 15. And so this is our final end. This is our end of the base unit. This is our start. And once again, that's all the information we have. So that's how we see all the changes here. We got amplitude change to 1/2. We have center line at -2. And we have the periods being 2 pi over 3. And we have a phase shift where it caused our start of the period interval, or it caused our start of the base units being at x equals pi over 15. And this phase shift is also going to cause our end of the base units being at to become at 11 pi over 15. And that's how we recognize all that changes happen to this graph. And now we can confirm the transformations found in the function minus 1/2 sine of -3x plus pi over 5 minus 2 by looking at its graph. And so once again, my base unit of the sine function in red color is here. And now let me bring up the base unit for our current function minus 1/2 sine of -3x plus pi over 5 minus 2 being in blue. in its base unit. And so now comparing the two graphs. So first of all, this graph in blue has center line at y equals -2, as we already found. So now I'm going to put that center line being in black color, dotted black color here. And so compare with the original version. This graph here, this wave in blue, is being moved down or being brought down by vertically by 2 units down compared to the original center line here. So this new center line in dotted black color is at y equals -2. The amplitude of this blue wave is only 1/2, and you can see that here is -2 vertically and here is -1 vertically. And so this wave in blue right here is only half units up and half units down away from the center line, and that's why that's how we recognize that the amplitude of the wave here is being only a 1/2. And this wave in blue right here has starts. We already found that the start and end of this base unit here being, now the grid here cannot show all that, so let me put the actual start and end point of our on the center line here of our blue wave here to show the labels. But the start here is at x equals pi over 15, and the end of our base unit here on the blue wave is at 11 pi over 15. And so subtracting the two values here, subtracting the start from the end value, then we have a period being a 2 pi over 3. And that is consistent with what we identify as the transformation. Our transformation here made the graph having a shorter period compared to the original period on the original sine of x. And so now in the complete graph here, sine of x in the complete graph is there, and now the complete graph of our minus 1/2 sine of -3x plus pi over pi minus 2 is here. And once again, I could have also mentioned that the orientation of our graph in blue here is exactly the same as our ordinary sine of x function, because there were no reflection through the x-axis.